Okay, I will. All right, well, thank you for that. I'm gonna upload real quick a couple things and then get rolling this, but what I want to upload is, I mean, I'll toss the handout for today's lecture. You should probably have from yesterday, but just in case. But then the other things I want to upload, I think it's critical. I mean, I know you can download this from AAMC, but I'm not sure everybody does it. But it's the topics for the chem physics, and then also the topics for the bio section. And just really important, I think, is, well, I mean, for whatever reasons, you should always double check whatever anybody tells you. So if somebody says, this is definitely on the MCAT, this is always on the MCAT, double check and make sure. I mean, there are certain things, like obviously electrochemistry always shows up. Amino acids always shows up. I think there's no doubt about that. But there's some topics in physics that maybe aren't as popular as you were being led to believe. And so just double check that those things are there. It's just good to do your own due diligence. So those are the official guides that you can download from AAMC website. So have all of you done that, by the way? Was that on your to-do list? Okay, always a good idea. And if nothing else, just to keep an ongoing checklist, as every time you finish a topic, cross it out in one color. When you review it with homework, cross it out again. And when you feel good about it, cross that out again. And that way you just have a good idea of just where you're at. Okay, so titrations and indicators. Oh yeah, print it out, I think is better. I mean, I have the book form, but anyway you have it, it's great. Okay, so titration curves and indicators. Titration curves are the systematic quantitative addition of one reactant to another. And so I'm going to do acid-base titration curves where you start with like an acid in solution of unknown quantity and you titrate it with a base. But could you also do an oxidizing agent, reducing agent? Could you do a nucleophile with an electrophile? In theory, can you titrate any one thing that reacts with another? Yeah, so I mean, in theory, you can do anything. So I'm going to focus on acid-base today, but keep in mind, they have in the past put electrochemistry ones where you had a redox reaction, oxidizing agent reacting with a reducing agent. The trick in redox, they're not always one-to-one, whereas acid-base is one-to-one. And then years ago, and I think they were just being crazy mean, they had a nucleophile titrated by an electrophile. And again, it was one-to-one, and it just was what it was. So I want to do the titration curves for acid-base, but you need to be open-minded enough to say, yep, they can apply this to anything. Okay, so titration curves and indicators. So what's an indicator? Before I click into what it is, what does an indicator do? Gives me some indication of something. And so I want to start by just asking, if you had a diprotic acid, do you react? Do you deprotonate or neutralize both protons at the same time? Or do you do the first proton completely and then the second proton? Sequential. You do the first one. When that's done, then you do the second one. So you do the strongest one first. So how many would definitely agree strong, or I'm not going to say strong, just diprotic curves? How many agree you have one curve like this for the first proton and the second one like this, which really doesn't start until you've taken the first one off? Okay, so I'm going to mess with you. Again, that's job satisfaction. Let's say I had something with one proton, but then I added an indicator in there. Would it make sense that you would, if the acid is stronger than the indicator, that it would take the acid first, and then once the acid is done, then it would take the indicator? But the indicator we put in high or low concentration. But the indicator is such low concentration, so it's kind of a funky curve. I have my first graph here. This one should be smaller than that. I actually wrote it like this. This is way more than you should actually add. But basically, is the indicator kind of like a second proton that you don't start reacting until you've completed the first proton? So if you think like that, it just happens to be a second proton. So not until you completely neutralize this one will you start seeing the second one. And so if the second one is one color here and a different color here, then can you see a rapid color change if there's just one drop? So after you completely neutralize the acid, that next drop is going to go from one color to another color very quickly. And how many definitely noticed that? How many would agree the "is it pink yet" lab was the "oh damn it's pink yet" lab? Yeah, I mean, I butchered the heck out of that. So, I mean, based on my horrible titration skills, I actually had the head of the whole chem department come in and like ask like what my major was. When I said a chem major, this is my freshman year, he looked at me and said, "Well, have you considered something else?" And so, yeah, you're traumatized. I think I'm definitely traumatized. And the irony of it all is I ended up being a TA sophomore year for that class. So clearly they know it's BS. But for what it's worth, yep, you have this tiny little drop that gets neutralized. So first proton gets taken, second one then gets taken very quickly because you just have one drop. So indicators, I'm going to get rid of what I've written here. In indicators, there's two ways we're going to look at indicators. They're used for two things. One, like we just mentioned, detect the endpoint. So once the first proton is completely consumed, they react and get a rapid color change, so you see that. But also, how many have ever seen, like for fish tanks, swimming pools, even in lab, those little test kits where you drop it on a piece of paper and it turns some color and you estimate the pH from the color? Yep. Those are also indicators, but those are a little bit different. Those are usually an indicator where, let's say, the protonated form is one primary color, such as yellow. The deprotonated form is another primary color, like blue. So really, are there two color changes from yellow to green and then green to blue? So would this be a much broader, instead of something like clear to pink, colorless to colored, there's really only one transition, one color change. The one color change, great for detecting an endpoint titration. But if you want to estimate the pH of something, what happens when it's perfectly green? Is green more blue, more yellow, or exact balance of both of them? So if I mix exactly the same amount of yellow and blue, how many do you get a balanced mixture? You get green. So when it's balanced, when you have equal amount of protonated and deprotonated, according to the Henderson-Hosbach equation, pH equals pKa. So let's say the pK of the indicator was 8. Then if this was the color of the solution, it was pH of 8. If it's up here, maybe it's 9. If it's up here, it's maybe 10. If it's down here, it's maybe 7. Down here, maybe 6. So how many have done that as well? Looked at one of those pH strips, those pieces of pH paper, looked at the color, compared it to the back of the panel, and made a guess at what pH it was. Okay, so at least one person. Or, I mean, it's way too personal example, and I don't want you to actually answer this, but have any of you ever had to have a urine sample done where you had to pee on a stick and see what colors things changed? Either you're a pro athlete being drug tested, option one, or they're testing for something and just looking at simple pH tests when you pee. So, okay, so yeah, and I mean, the same sort of thing. Sometimes those tests have other markers on there. A lot of times, just a piece of pH paper. Ketone bodies, exactly. So possibly, I mean, it could be potentially a test for diabetes, amongst other things, but also could be other metabolites. So perfect. Okay, so feeling pretty good about this. And again, just want to revisit something I was saying. So for some of you who ducked in a little after the start, these are the official topics from AAMC list that correspond to acid base. And I just think it's really important. I really want to stress this with all of you, that if you can, Jonathan, can you scroll up? Because I can't move my cursor right now. I'm trying. There we go. I think I got it. Okay, so just really want to add, especially at this point, you should double check with the AAMC list. So anybody who was here early and got it, would you mind putting it in the chat box so other people can get those as well in case they haven't? You can download it from AAMC. It's an easy search and download, but in case you didn't, this comes from the one for the chem physics section. Okay, perfect. Thanks for putting in Discord. I appreciate that. So the things that I'm interested today are definitely indicators, neutralization, interpretation, titration curves, especially for amino acids. So that's what they like to add. But other things that are also of critical importance, do you actually have to know your strong acids? Yeah, and what curves they're going to look like. You need to know your weak acids. And then these I'm going to put little dots next to because these just sort of happen. I don't know if we actually have to make a conscious effort, but they will. You should have, we'll have a buffered section in the curve. So definitely we'll look at this part. And then knowing what ions are in solution along the course of the pathway is important. This is actually, doesn't apply to this. This just happened to be the page 17 and page 18. But double check. And so just want to just say, this is what we're aiming for. We're trying to check things off this list. Anything I haven't circled, conjugate pairs kind of will show up with buffers a little bit here, but it's kind of its own separate thing. Make sure you look at these. So make sure what we did last week, we covered all these. pH calculations have popped up on some of the homework, but just make sure you're checking your list off. Okay. So on to titration curves. The basic concept, and again, I'm only going to do acid-base titration today, but note you can titrate anything with anything. If something reacts with another something, you can do this process. So you're doing it to figure out exactly how much of something you have. So if I have an unknown molarity of an acid, and I put, let's say, an exact volume, 25 milliliters into a flask, a beaker, some sort of container, and I quantitatively add a base of known concentration, the second that I've added the exact mole quantity of base to the mole quantity of acid, will end up neutralizing the acid completely. And from there, I can figure out exactly what the molarity of the acid must have been in order to have equal number of moles. So in other words, the moles of acid initially present equal the moles of base I added. And I just need a quick review. I've already forgotten. What are the units of molarity? Sorry, I'm trying to find the move or add button here, but I'm struggling. Okay, so the units of molarity, moles, solute, liters of solution. Man. Okay, so what if I multiplied m times v do I get? What are the units if I do that? So moles per liter times units volume liters. Just moles. So if the moles of acid initially present equal the moles of base added in, is it possible to say mv for the acid equals mv for the base, m1v1 equals m2v2? So how many have had that equation beaten into you from early on in chemistry and it hasn't really gone away? M1v1 equals M2v2 for dilution, for titration, for any sort of interaction. So critical to know that. So that's what we're going to get at. So I'm going to get rid of this, and then we're going to systematically figure out what's happening. So what's your prediction if I add a strong acid and a strong base exactly equal? Will I end up with an acidic solution, a basic solution, or a neutral pH 7 solution? Neutral. So what we mean by equivalent is equivalent moles. So if I have 7 moles of acid, one equivalent would be 7 moles. If I have half a mole of acid, one equivalent would be half a mole. So the equivalent is a lazy way of saying an equal mole quantity. So I'm going to tell you then, I'm going to predict that that circle right there is where it should pass at equilibrium. So we'll see if this happens. So when I add the acid, my circle is off, sorry. Acid goes up, pH goes up a little bit because it's a log scale, not much. And then all of a sudden, When I start running out of acid, it shoots up rapidly and then levels off and becomes the pH of the excess base. But let me get rid of my circle and put it in a better spot. So somewhere around there, known as the equivalence point. Okay, a few things you have to recognize. It fully dissociates, so it starts out flat. pH doesn't change much again because of the log scale. So it stays relatively flat and then it curves up and flattens out. So this looks like an S, but instead of just saying S, what do they call it? Sigmoidal. So S shape. So it looks like a sigma, like an S. So sigmoidal curve, stays relatively flat, climbs up, reach this. And then just want to revisit the concept of neutralization. Again, equal moles of acid equal moles of base. So at equivalence, by definition, the equivalence point, when it's neutralized, the moles of acid initially present, the moles of HX you initially have in there, equal the moles of base you've added in to reach that point. Moles equals moles. Yeah, sorry. So I apologize that it took so long to let you in, but it's basically me trying to find the circle with my cursor that I can't see. So again, I do want to apologize way in advance during office hours. If I ever launch you out and evict you, it's simply because I got my cursor in the wrong spot. Oh, no worries. So hopefully this is a low key. Friday should be low key day. Yeah, I think Zoom does do host first, co-host second. There is kind of a lag. So I noticed that co-host before. Okay, so as we go on then, so I have this equal part. Again, M1 V1 equals M2 V2. So M of acid, volume of acid, M of base, V of base. So let's revisit that painful memory called titration lab. And I'm going to do that by saying I put an exact volume of acid and titrate with a known molarity of base. So typical experiment, you know this and you know this. You can only have one unknown, so I need to do something with this. So we quantitatively, drop by drop, add in the base until we get that equivalence point, the color change associated with it. So this is a known, this is a known, this is measured from the burette. So basically, are we solving for the one unknown, molarity of the acid? So for all of you who did that, how many got it wrong? How many still didn't manage to get this right for whatever reason? Color was off, equipment was faulty, whatever it might have been. Did anybody overshoot it and make it really purple? Yep. And you had a professor or a lab TA that said, do it again. Oh yeah. I mean, and the thing is, that you don't know what you're looking at till you've seen it. All the TAs in the world, all the teachers in the world can tell you, okay, you're gonna start seeing a slight hint of pink, it's not gonna stay, then a little bit closer, it's not gonna stay, and then finally it'll stay. That doesn't mean anything to you. It's clear, 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 damn purple. Okay, what they did a hop skip in a few years back is they talked about a different way to set this up. I'm gonna go back to that graph in a second, but they said, instead of adding with a pipette, use a burette. So you add in the acid, and then titrate it. If you over titrate it, add a little acid back in. This is a concept known as back titrating. Put this one in, then if you titrate it and overshoot it, then just add a little here, you overshoot that one, go back and forth until you get the exact pink color you want. Did anybody have a TA that made you do it this way, or a professor made you do it this way? Ah, brilliant. Wow, really? It was more fun, except more glassware cleanup. But yeah, this is such a better way to do it. Okay. Well, I don't know how to read this meniscus. And I think they call it a kneecap, something like that. Do I read the top or bottom of the meniscus? What is convention? Silly question. Can't believe I'm asking it, but yep, that's what they asked. You read the bottom of the meniscus. Okay. The key thing, you got to be consistent, but it's easier to see the bottom than it is the top. Okay. So I'm going to add in some acid, goes in, and then I'm going to titrate it with base. And because I am so awesome at lab, watch this just go perfectly neutralized. Wow. So yeah, money time on this one. So worked out perfect. So here's my question for you. We titrated with a known molarity here. What is the molarity of that acid? You have 10 seconds or less to get it right. So I'm curious if anybody can get it. I'm not going to tell you anything. You got to get that for yourself. Dang it. Oh, maybe I'll tell you. So does anybody feel like you can get this in 10 seconds? And I loved this question when I heard about it. Can only estimate. The answers look really precise, but they're actually not. So you could calculate every line if you wanted to, but both of them started up here. Which should I add more of, the acid or the base? Okay, so let me see if I understand this right. I'm going to put this in here as molarity of the HCl. I'm going to call this a little less equals 0.110 times a little more. How many would agree that's some pretty imprecise math? But how many would agree 0.110, that was a given. This one I'm solving for. And this number is a little bit smaller than this number. So what can you tell me about that number right there then? Is it higher or lower than 0.110? Has to be greater than 0.110 molar. So I know that by a lot or a little. How many are okay with that? And honestly, on the test, do you think most people would sit there and count the lines and try to figure out the volume? Which would work. It would definitely work if you calculate 5, 10, 15, 20, 25, 30, 35, 40, 46 maybe? Did I do it right? 10, 20, 30, 40, about 46-ish. 10, 20, 30, 40, 53. So if I plugged in 46 and 53, math would still suck, but I'd still be guesstimating, but I'd see there. Yep, visualizing it. The cool thing about this question is the exact same thing you did in school, but visual instead of numbers on a page. So is it exactly what you learned in school, but presented differently? And it's both kind of cool and stressful. And how many does this stress you out, that you're going to look at things you don't recognize, even though it's stuff you've seen before, but in a different mode? The different ways you look at things, the better you get. The more you look at things, the better you get. So does this question make sense? Does this approach seem reasonable to you? Because it solidifies that relationship, MV equals MV, but it also makes it kind of different, kind of twisted just enough that you have to trust that relationship to figure this one out. So it's got to be a little bit more in 0.110 because it's a little less volume needed. So it must be a little less volume, so a little more concentrated. Yeah, and if you wanted to, you could definitely put an arbitrary number. So I did exactly 46 and 53 when I just counted it. But if you wanted to put a number like 45 and 50, something like that, that would work too. And how many do that? How many, when putting an arbitrary number, it just makes you think in numbers to see a number? Then by all means do that. Definitely a good approach. And I gotta admit, I always have to do that. When something is going square or increase by like a square root, I always have to plug in numbers 2 and 4, 3 and 9, 4 and 16. To plug in numbers to see a trend. And it works. It gets you an answer and you make good choices in a timely fashion. Okay, so this concept, this came possibly on a passage that was about back titration. So back titration, let's say we did overshoot it. Where would I add the extra acid? Would I put it on the acid side or base side? So let's say I over titrate, make it way too pink, add a little more acid in. How do I account for that calculation wise? The total moles of acid stay together, the total moles of base. So if you have to back titrate, if you have to have your initial amount, you over titrate it here, simply add the moles here. So total moles of acid added in to start plus back titrated equal total moles of base needed to reach the perfect pink. Okay, how many feel okay about this? I mean, there's some numbers that'll go with it. We'll look at numbers, but at least the general concept hopefully sounds somewhat familiar in theory. Luckily, you don't have to make a pink solution, but in theory, it's looking pretty good. Can I titrate a strong base with a strong acid? 8 out of 10? I'll take it. Wouldn't do well in gymnastics, but I'll still take it. Sure. What would be different about it? Would it still be so sigmoidal? Yeah. And would it still have pH of 7 at equivalence? Yeah. It just would start with base instead of acid. So it would look kind of like that. So strong curves, I want you to just note a few things. Strong curves, there's two things to note immediately. They're sigmoidal. They start out flat, they have a drastic change, and they finish flat. They look like an S or an inverted S. pH of 7 equals equivalence. You know these two things automatically. Anytime you look at a strong curve, you know this. The last thing I want to add that I think, and this popped up last class, but I'll just reiterate it here, the pH of a strong acid. It's also going to be pH of a strong acid equals negative of the power of 10 minus log of the mantissa, which I don't know how to spell mantissa, so I'm going to say unit number. And I'm going to plug in what I mean by this. If I have 3 times 10 to the minus 2 molar HCl, what is the pH? Two, the negative of the power of 10 minus log of 3, 2, 3, 5, 7, 2, 3, 5, 7, 8, 4. So I hope that we did this last time, and hopefully you've done a little bit of homework where you ran into this. But how many are okay with this quick solution to get the pH? Put it in the scientific notation, negative power 10 minus log the unit number. So perfect. And then the question popped up, the pH doesn't always have to be pH of 7 though. If it's a monoprotic, if it's only one strong proton and one strong base, yes, it is actually always 7. The exception to the rule, if it's a weak acid or weak base, then it won't be 7. So this isn't for all curves. This is specifically for a strong curve with a strong, and even more importantly, strong monoprotic. Like H2SO4 screws with us, but for nitric acid or hydrochloric acid or hydrobromic acid, so ones with one proton and they're strong, that'll be the case. So strong on strong. So sigmoidal curve, pH equals 7, and the pH in the beginning can be gotten from the molarity in this way. So let me throw one more question at you, and you have 15 seconds to get it. I need to write it first. Okay, finally. So pH of 11.72 milliliters of 0.0005 molar HBr. You should be done by now. So making you feel a little bit guilty and want to explain why you should be done by now. Because does this number matter? Not at all. Could have a lot of solution, hardly any, makes no difference. Don't care about that one. This number rewrites as 5 times 10 to the minus 4, 4 minus log 5. So get tripped up. Yeah, but when you get tripped up, you remember down the road. And I do feel a little bit guilty for how mean some of the questions are. I'm guilty of writing some mean questions, but this is one of those I have zero guilt because this is a really important skin your knee type experience. Skin your knee once, not gonna do it again. Volume doesn't matter. All that matters is the molarity. So how many are okay with this quick turbo method? Strong acid. So it fully dissociates, so 0.0005 is 5 times 10 to the minus 4. 4 becomes that number, minus log 5. We're set. Yeah, so the shortcut is basically this. So when I put the concentration in scientific notation, the power of 10 goes there, but negative of it because it's a negative log. So negative of a negative 2 just becomes 2. And then this number, let me do it in purple, I haven't used that yet. This number becomes that minus a log. The basic math of it, when you multiply numbers, you add their logs. Log of 10 to a power is just a power. That's why this power just comes down by itself. And then log of 3 is right there, but negative, because pH is a negative log of something. That's why the negative sign's kind of jacked up on this one. But this only works for strong acids or Kas, Kbs, and strong bases. I should say strong base as well, but strong reagents, yes. For weak reagents, they don't fully dissociate, so you can't quite do it that way. But we have a cool way to get weak ones. Okay, so 3 things. 1, sigmoidal shape. 2, pH 7 equivalents. 3, you get the pH using that shortcut. Okay, I put so much on this page, time to click on. So screenshot if you want to, but I'm moving onward and upward. 3, 2, 1. Weak acid. Does weak acid fully dissociate or partially dissociate? Can't remember what the definition is, but you're going to help me out. Partially dissociates, exactly. So rather than the pH starting way down here, it starts up here. It will climb for a while, and then is the HA turning into A minus over time? How many agree that as you're adding base, you're pulling the H off of HA and turning to A minus? What do you call a solution where you have HA, the acid, and A minus, its conjugate base? So is there something that exists when you have a weak acid, weak base in roughly equal parts? So you remember such a solution. Mixture of weak acid and weak conjugate base in roughly equal parts makes a buffer. Perfect, exactly. Somebody learned that. A buffer is a mixture of weak acid and weak conjugate base. They don't consume each other. They sit there and coexist. What is true of a buffer's pH? Easy to change or relatively constant? They stay constant. Okay, so should this be a straight line across, or should it be a slightly increasing line? What is a better description? Perfectly flat or relatively flat? Second one. Okay, and then you're going to climb up to the equivalence point. Curves need to be curved, so we'd agree this is kind of a weird thing, but it's going to climb, it's going to buffer, and it's going to climb. So here's what it's actually going to look like. Okay, so got the basic idea. So let me erase what I've written, but it climbs, check, stays relatively flat, check, and then climbs at the end. I'm going to leave that line there for a reason, but I have this. So is this curve a little bit different from the sigmoidal one? So if I got rid of this, once it reaches the buffer region, does it look sigmoidal? And how many agree that now that I've erased that beginning part, you agree it looks just like the strong curve? But the difference is that little bit of beginning. So I say this kind of looks like, if you've ever seen an ocean waves look kind of like that. This part is called the lip of the wave. So I call it the lip of this curve, the lip of weakness, because only a weak curve has a lip. So if it has a lip, it is weak. It initially climbs, then it levels off. So initial climb until it forms a buffer. Then this middle region, which, would you agree, the middle region makes up almost the entire curve? So it's a tiny climb in the beginning. It's essentially a buffer almost the whole time. And it's a climb at the end. Notice there's a slight change from what we just dealt with. And I want you to make a prediction. If I have a weak acid and a strong base, which is going to dominate? The weak acid or strong base? Strong base, which means if I mix equal parts, 1 mole weak acid and 1 mole strong base, is the solution going to be neutral, as in pH 7, or slightly basic? Slightly basic, which means the pH equivalence is now a little bit greater than 7. So the weaker the acid, it's going to be more dominant base, and the pH is going to be a little bit higher to equivalence. If they're perfectly equal, it goes back down to 7. So pH equivalence is greater than 7 for this curve. So it has a lip, it climbs. This one is not so predictable, I got to calculate it. But is there one point on this curve, just like there was on the last one? Is there one point that's very predictable? The answer is yes. And it's so amazingly complicated, this basic algebra, that it took two people to do it. So Henderson and Hasselhoff, or Hoffelding, or Hinkelheimer, whatever the names are, the HH buffer equation. I'm going to add the word buffer because I'm telling you, I love the fact that biochemistry names enzymes after the reaction. Makes it easier to understand. So I'm going to do the same thing. Take their lead, the Henderson-Hausbach buffer equation. So every time somebody says Henderson-Hausbach equation, I want you to insert the word buffer, because when do you use it? Use it when calculating the pH of a buffer. So this equation, pH equals pKa plus log of, can never remember, acid over base or base over acid? Aha. Aha. I should remember that. Molarity, technically, but like the band. I was going to say like the exclamation, but yeah. Wait a minute. Are you old enough to know that band? That's like way too personal a question. But please say you've heard it second, third, or fourth hand. So the pop culture thing. Oh, there was a revolutionary band, but yeah. Totally being ageist. Or actually, truth be told, totally fishing for somebody in my same age group. So I don't know if that's ageist or age magnetist, but it's a Norwegian band. They're Swedish. They're I think they were Norwegian, that did a song called "Take on Me," and they basically invented the cool video. Not ABBA, AHA, AHA. It's a band that they're famous for one song that completely revolutionized videos. Yeah, American Heart Association, when they were back in Norway doing music. Oh my gosh, Fabian, I'm jealous. That would have been such a cool concert to see. I hear they just were really good. But the point being, they're also a band and they're part of this equation. So base over acid. Yeah, that is true. I mean, they are a far more established band beyond our borders. And certainly in the Baltic, they're notably famous. They're really talented. But I'm being US centric, so sorry about that. And ageist. Okay, so at the halfway point, in the very beginning, I'm going to tell you it's all HA. At the very end, it's all A minus because you fully neutralize it. So what happens at halfway? What do you have? Equal. Okay. So what does aha equal when they're that way? One. Log of one is 0. Perfect. So at the halfway point, pH equals pK plus if A minus equals HA, if they're equal, that's 1. Log of 1 is 0, cancels out. How many have had this beaten into you in biochem? How many have just had that pound over your head repeatedly? Okay, so the things I know in this curve, I know it has a lip and pH equals pK. Perfect. I'm going to come up with a way to get the pH that I think is going to be a little bit easier. And so I'm going to ask you to trust something here. So let me write a curve like this. And we're going to do polyprotic curves in a bit, but I want to just totally overdo it. PK1, PK2. I so wish I had an option for a fine tip. So how many have learned that if you have multiple protons, that still pK is always in the middle? Here is something you learned in biochem. How many learn that is an average of pK1 plus pK2 over 2? How many definitely learned something like that? You average 2 pKs surrounding pKs and get that middle point? Okay. It ends up, I'm going to steal that same thing. Time out. Let me get my numbers straight. pK2 plus pK3 over 2. pH equals pK3, pK4 over 2. If you can't read this because I can't read it, I'm right next to it. That's pK4. I just went off the page. Sorry about this. Okay. So question has popped up. Great question. This one is actually a really common question that we just sort of, I think, honestly, nobody ever asked, even though they should. What is the difference between pH and pKa? So let me ask you a weird question that hopefully will tie back into this. What is the difference between a melting point and a temperature? They're both the exact same units. You agree pH and pK are the exact same range. Okay, which one's a phase change, the temperature or the melting point? So change of matter, change of state. Melting point is a physical property, and it definitely comes in units of Celsius, Kelvin, whatever you want to call it. What is temperature? An average kinetic energy of the compound or everything around it? So, measure of the energy of the surrounding system. So whether something's melted or not depends on the temperature, the melting point, or both. Both. Okay. Which is a physical property of the compound, the pKa or the pH? So which one is a physical property of the compound, pKa? Which one is a measure of the environment? pH. Just like temperature affects the melting point, melts it or doesn't melt it, pH, the environment, affects the compound. So if something has a low pK, it's highly acidic. If something has medium pK, it's medium acidic. It has a high pK, it's weakly acidic. Something has a low melting point, easily melted. Some medium melting point, medium to melt. Some high melting point, hard to melt. So just like you have to adapt the temperature to melt something, you have to adjust the pH to deprotonate something. So pH, yeah. Okay, can I repeat the private message just popped up? You mind if I quote you? Okay, so oh, it's ironic when you responded sure, that like knocked it out of you. I have my screen set up weird, but so the quote was, "Wow, I've not thought about it like that. Thank you to whoever asked that question." And that's it. I really want to point that out. That's a friggin' phenomenal question because it's a good way to view this of what it is. And a lot of people I don't think fully grasp that that's kind of what it is. It's just a measurement. So if it's a really strong acid, what's true of its pK? Medium, high, low? Very low. So it's going to be deprotonated at a low pH. You don't have to raise the pH very much to deprotonate it. So it's going to be deprotonated maybe 2 or 3. Oh, so pK is a physical property basically measuring how easily does it lose a proton? How acidic is it? And so that's when I ask the question, what is the pK for a strong acid? Well, strong acid loses its pK or loses proton very easily. So its pK is very low. Just like something that melts very easily, its melting point is very low. So pK low means it loses a proton very easily. A really high pK means it holds on to that proton. It doesn't lose it very easily. It can lose it, but it has to be extremely basic conditions. And so whether something's going to be protonated or deprotonated comes down completely to, is the pH higher or lower than the pK? Just like if it's melted, is the temperature higher or lower than the melting point? And so hopefully that correlation makes some semblance of sense. So pK is a measure of how acidic it is. Weak acids have higher pKs. So if I was titrating a weaker acid, same shape curve, but it would be higher at this point. If I was doing a stronger weak acid, it'd start lower, have a lower pK, and finish like that. So where this point is, higher it is, weaker the acid, lower it is, the stronger the acid. So does that seem okay? And definitely, thank you for asking that question. That's a freaking awesome question. And it hopefully clarifies things. Okay, so let's consider that. So a strong acid in a very basic environment would not lose H plus. Other way around. So tell me, if it's a strong acid, what's its pK, high or low? Very low pK. And if it's a basic environment, is that a high or low pH? High pH. So if you have a really high pH and a really low pKa, they're drastically different. It's going to lose it all. It's going to lose everything. So as long as pH is higher than pK, that means it's a basic environment. It will steal the protons from the compound. It'll lose its H. So, and in that case, an acid in a basic environment will be completely deprotonated. Yeah, exactly. So pK for a strong acid is very low because it loses it very easily. For weak acid, it's higher because it doesn't lose it as easily. And so if you just think of it on that scale of how, on a scale, if I ask you, on a scale of 0 to 14, how hard is it to take the proton? Is that kind of what we just created? Yeah, I'm so glad it makes sense like that. But really, I mean, it sounds silly to word it that way, but literally what chemists are asking you, okay, fine. On a scale of 0 to 14, how easily does it lose that proton? So for a carboxyl terminal, now 2 to 3. So it loses it pretty easily. That's why it's the first one to go in a protein. On a scale of 0 to 14, how easily does the amino terminal lose it? 9 to 10. It's just rating how easy it is to lose that proton. And when you think about it that way, does it become a lot easier to deal with? This elusive weird number is just basically an identifying mark. Jonathan, do you see somebody on screen? Because my cursor is now messed. Oh no, my cursor's back now. Oh no. Oh, you let. Nice. You were fast on the draw. Thank you for that. Okay. So for this one, how many have definitely learned you average 2 pKs? That sounds familiar. Now I want to screw with you because again, job satisfaction. Can I get this point up here somehow? This one is kind of weird. Nobody ever teaches this, but yeah, you can. You have to average this. So what do I have at this point up here? Do you agree? I've already over titrated and it's just excess base. Yeah, 14-ish. And the reason I can't agree to 14 is because I didn't have enough information to know exactly what the molarity is. So if the molarity was 1 molar, then it would be 14. But let's say the molarity was 0.1, it'd be 13. So you're totally on the right ballpark. I just don't have enough information to confirm 14, but I am going to say high. So can I just say the pH of the base? Which means, tell me how you get that point right there. Same way you did it for all the other ones. So it is so simple to use a curve to summarize numbers, but this you've got from biochem. The middle equivalence point is an average of pKs. Middle equivalence point, average pKs. Middle average. This one is an average of the pK and the pH you titrate with. This one down here, the last one I'll do, the starting point right here, is an average of pK1 plus the pH if fully dissociated, if we're strong.
Jonathan T said
this
tenor
one is weird. This one bothers people. But it's still an average of what would have been there. Yeah, we're solving for the pH. So pH is that, pH is that, pH is that. You're so right. I forgot to write pH equals. Oh, shoot. Let me. One bit. Uh-oh, and I messed this one up. Divided by 2. Okay. I'm so sorry to squeeze this into such a small space, but hopefully this seems okay. These I get from biochem. This is a new thought. This is a new thought. So let me know when it's okay to erase this entire curve. So if you screenshotted it, let me know, because I want to move on and take this point and put it here, and take this point and put it here. So free to erase. Yeah, so I'm going to hold off on fully dissociated. I'm not going to, so 2 people have asked me, can you explain what this one is? I'm going to hold off on this until I do it right here, because it's too cramped in here. I can't see it. I haven't done a good job. So this one, it's way too confusing. What the heck's going on? So it's going to be easier here. So is it okay if I erase this picture? Okay, 1 yes vote. I'll go with yes. Anything you need to know then? It's going to screenshot in 3, 2, 1, gone. Let me reiterate lip. pH equal pK. And then now I'm going to try to figure out what is the pH at this point and this point up here. So this point here is an average of the pKa and the pH of the titrant. Okay. This one down here is the funky weird one. This is an average also of pK but now if it were strong, if it fully dissociated, meaning if we're a strong acid and it completely dissociated, do you agree the pH would be lower? So this is what it would be if it fully dissociated. Is this point here roughly halfway between here and here? So if it fully dissociated, it's right there. So pH, I'm going to just simply put if it were actually a strong acid. So if we're a strong acid, if fully dissociated, be there. That's what we meant by figuring out the pH. It's a quick and easy way using your curve. You're doing the same thing you did in biochem, but now you're creating a point here. So this is an average of pK and the titrant base. This right here is an average of pK and the acid of the same molarity of the base you're using. So for instance, Brooke earlier said, maybe this is 14. So if this is 14, this would be 0. Because if it's 14, 1 molar here, it would have been 0 down there. So 0 plus pK would give me this, divided by 2. 14 plus pK divided by 2 would give me that pH. So does that make sense what we mean by this? The molarity. And it's a weird sort of shortcut. And what I'm assuming the motion is right now is how many say, I can see it, but I don't really feel it yet. So when I say pK, why am I not saying pK1? Really good point. Why am I not putting the 1 in there? Because there's only 1. So there's no second one yet. It's just like, could I put the name senior at the end of my name? But if I put senior at the end of my name, that implies there's a second one after me. So you can't do it until there is a second one. So unless you have a kid with your exact same name, and your parents not the same name. I don't know if this is the best analogy. So perfect. I'm going to revisit this thought. This is a little bit unnerving, but it's based on the symmetry of the curve. So this equivalence point is an average of the base, the pK. This starting point is an average of the base and the acid, the strong acid point, the strong base point, and pK. You average those two to get this one, those two to get this one. So how many are kind of okay with this? How many are like, yeah, I could sort of go through it, but it's not perfect? Yeah. So when you step out for a second.
Sorry, I just meant like if we can look at the big picture for a second. I think I got
Oh,
lost
yeah,
in the
yeah.
details, and
Okay,
I'm
yeah.
a little confused what the focus is.
The whole focus is going to be, when they ask me a question, what is the pH? I have two choices. I can punch in numbers and calculate it using different formulas that apply at different points, or I can bullshit my way through and guesstimate what the number is using the curve. And so the big picture is going to be, forget calculations, let's BS our way through it. That's basically what we're getting at. And so this is like a lazy alternative to using math. And actually, that's a really important question. How many do exactly that? How many say, timeout, why? What's going on? What's the big picture? Why am I worried about this minute tree? What's going on over here in the forest? Definitely. So efficient, not lazy. I know lazy just sounds, I don't know, self-depreciating, makes it seem better, but yeah, it is a more efficient way to go through it. Okay, then if it's okay, I'm going to totally turbo through real quickly and cut to the chase of why we're doing it. So yeah, I just got so caught up in the details, and you're absolutely right. Okay, so here's why we're doing it. This is going to be complete information overload at first, and I'm going to erase everything. 3, 2, 1, erased. And so this is on the handout, but I want to point out what's going on with this. This is the big picture, overwhelming. But if somebody has a lot of information, you have a midterm coming up, they're your friend, you have a test coming up, there's lots of information here, this is your friend. Here's how we're going to use it. I'm going to give you a scenario, and you're going to start telling me what the approximate pH is. When the acid is 37% titrated, where am I on that curve? So you agree 50%, I know pH equals pK. Is 37% beyond or in front of 50%? First half the buffer region, exactly. So how many agree? 37, maybe somewhere around there. So give me a guess. Okay, so why not the second? It takes 100% to fully get here. So if I've only gone 37% of the way, I haven't gotten to 50%, the halfway point. So the first half of the buffer region is before 50%. Second half of the buffer region is after 50%. So this is basically from about, the lip is about the first 10%. Technically, it's like the first 9%. The climb is the last 9%. And this buffer region's the middle 80. First half is before 50%. This one's after 50%. So how many agree this would equal to PK minus a tiny bit? PK was 7, it'd be 6.9-ish, 6.8-ish. PK was 4, it'd be 3.8, 3.9. How many can guess the pH if you know that this is +1, this is -1, and this is PK, and this is an average of whatever the acid would be, this is in that right there. So does this seem okay how to look at the curve and guess what the pH is? We're using it as an alternative method. Okay, so 2 positives. I'm going to move one step further and see if I can actually do it. Let's put this into action. So it is information overload. Do not freak out yet. Let's apply it and then trust it. So as long as I know that's pKa, that's -1, that's +1, we're going to be in pretty good shape. So for instance, if I titrated a weak acid, 0.125 molar with 0.125 molar KOH, if I have 50 milliliters of acid at this concentration, how many milliliters of base at that concentration do I need to reach equivalence? So if I did M1V1 equals M2V2, perfect. So 0.125 times 50, sorry, oops. $32, we already know that, sorry, is 0.125 for the base. V2, 50 equals V2. Perfect, so that means down here I get a 50. Okay. Erasing in 3, 2, 1. I'm at 50. What is half of 50? 25. Perfect. So if they tell us, they have to tell us this, but if the PK is 5, that means if I have 25, I'm at 5. What is 5 minus 1? 4. And what's 5 plus 1? 6. So the buffer region is from 4, 1 lower than 5, to 6. What is 10% of 50? Just move the dot over. 5. And then 90% is 100% minus 10. So 50 minus 5 would be 45. So these numbers fall into place pretty easily. This one I'm not going to worry about. This one I'm not going to worry about. But if they tell me this, if I have that information, then let's say they give me a question like this. What is the pH if we've only added 18.6 milliliters and not the full 50? So we need 50, but I've only added 18.6. What is the pH? Perfect. So, another good answer. Yep, exactly. So somewhere in that region, somewhere between 4 and 5. So for this one, 18.6 is less. 18.6 is going to fall somewhere around there. Beautiful. Okay, and then what Jonathan's trick, did anybody realize what Jonathan's trick was? If it took 50 milliliters, 50 times 2 is 100, so 100% titrated. So 18 times 2 would be 37-ish, 37%. Same question asked before. Okay, what if I did this? So 4.7, 4.8, perfect, if you knew those numbers. And how many would like multiple choice options, make it a little more realistic? So this one, where would you end up? Got a C vote? Got a B vote? So C's and B's are coming in. Where would you see 37? Number 37.9 is probably around here. So somewhere in that region. So perfect. You forgot to double it for your method. So you need to double the 37.9 to get the percentage if you're doing your method. Yep. So 37.9 is here. So best answer down there. Not perfect, but how many can do that pretty quickly? How many get the pH reasonably quickly? Is this faster than using the Henderson-Hausbach equation? That's the big picture of it. So titration curves, revisit it. Weak ones have a lip, pH equals pK at the halfway point, and then you can use it to estimate the pH. Okay, so with that in mind, I want to shift gears and mess with you in the way I like to mess with you. So 3, 2, 1, clicking. I want to put a whole bunch of curves on one graph. So tell me about this curve. Is this strong with strong or weak with strong? Strong, strong. Lip or no lip? No lip, it's sigmoidal. Perfect. pH 50 milliliters plus 0.1 plus 0.1 is going to require 50 milliliters. What's a pH when I've added 50 milliliters then? 7. Weak acid has lip, strong acids do not. Okay, in this case, is it still going to be a sigmoidal curve? Is it still strong acid, strong base? Still sigmoidal, always sigmoidal, and pH equivalence is still 7. But in this case, do I need 50 milliliters to get to 7? Or because it's more concentrated, do I need less than 50? Less than 50 in this case. Because 50 of something small is going to equal less than 50 of something big. So for this one, we only need 25. 25 because half the molarity would require double the volume. So 0.1 is half of 0.2, so 50 is double of 25. Okay, for this one, switching around on you. Now I'm using a lower molarity base than acid. So now how many milliliters do I need to reach equivalence for the green curve? 100, perfect. So let me go ahead and click that in just a second. And then finally, where's the blue curve going to end up? Same as a black, only slight variation, and that is, should it start a little bit lower than the black and finish with the red, just because of molarity, but exact same as black, passes in the middle. So which of these curves was sigmoidal? All of them. Which one has a pH of 7 at equivalence? All of them. The whole point, the strong curves, strong acid, strong base, doesn't matter what molarity, they can elongate, they can compress, they can do whatever you want. The two things that are true, sigmoidal with no lip, pH equals 7 at equivalence. So should you try to know a lot, or should you try to know a little and be able to apply a lot? Option 2, don't overwhelm yourself with volume, learn how to apply it. Know little, apply a lot. This next question, I want you to, before you go into this next question, want to tell me the following things that are true. What do I recognize on a strong curve? What are the features of a strong curve? There aren't a lot, but when I look at a strong curve, no lip, sigmoidal, and One other feature I know for sure. pH equals 7 in equivalence. Exactly. What do I know about a weak curve? Lip. And what else? What's the other thing I know about every weak curve? pH equals pK at the halfway point. Those 4 things are all you need to get a really tough question like this right. So I'll talk to you in about a minute and a half. Perfect. I cruise away for a second, but oh, I know the timer. It was on. It just weird the way it glitches, so it came in surprise at the end. So sorry about that. But yeah, all the answers submitted. Totally right. How many had no idea where to start, other than let out a few profanities? So this one, just like, what the heck is going on? Okay, your goal is to keep things challenging or simple. What is, at least as far as this test goes, keep it simple. So again, repeat to me, what do I know about a strong curve? Because I did something neat. No lip. And what's the second thing you know? pH is 7. Are any of these 3 curves strong? HJ, how do you know? No lip. So what's the one point I know on this curve? 7. What I did to screw with you, the evil mean thing I didn't label the y-axis. Made it much harder. But luckily, you knew this point. Tell me about the pink curve and the gray curve. Weak or strong? Weak. How do you know? They have a lip. What's the one point you know on both those curves automatically then, without any effort? pH equals pK. Perfect. Did you use anything complex, or are these the absolute basics? They're the fundamentals, the simple things. Don't try to overthink, try to underthink. Whenever challenged, find the easy solution, not the hard one. So, Iman, how did you pick your answer? Sorry to single you out, but your name just happens to be the first one on my list. I just looked up, so sorry to just seriously, just you just happen to be the top of the way my chat box is set up right now, or the participant list. So, and actually open to anybody. Perfect. You mean to tell me you know that this pK is less than 7, this pK is greater than 7, simply by on where they're positioned. Okay, and you're looking for something that is true or not true. So, is this reasonable that this one could potentially be correct. Is that reasonable? That could be 4.46. Sure. Is it reasonable that this one could be 6.7 or 6.96? Nope, it's got to be above. So this is my not true statement. When you look at this after seeing the answer, how many like forehead slap? Yeah, we'll look at A, B, C, and D in just a second. But how many, when you look at that, would agree that that actually is based on the absolute minimum of what I need to know? This is a really tough question because I messed with you. I got rid of the y-axis. But is it solvable by challenging advanced concepts or the very basics applied step at a time systematically? Know your fundamentals, know your basics, and apply them. Don't overthink, underthink. It's a weird message to send you, but underthink, process things as best you can. Okay, so let's go one by one and analyze it. So choice A is this point right here. Choice B is this point right here. So right when they're starting out. So choices A and B are the start. So this is choice A, choice B, choice C, and choice D. Is, according to this curve, is it reasonable that this is 2.23? Does that seem numerically viable based on where it's located? Yeah, it's reasonable enough. So I'll say that one's fine. That's okay. Is this one potentially 4.03? Is that number right there? If that's 7, and let's say that 0 down there, could that be around 4.03? Sure, that one's in the ballpark. Is this one potentially 4.46? We just went through that one. That one seemed close enough. So it seems okay. But this one cannot be true. This has to be greater than 7, cannot be equal to 6.96. So best answer was in fact D, as in damn. Exactly half, exactly. So the halfway point is when pH equals pK. Not the start, not the end, but the halfway point. But better learn that now. So does this seem okay, this question? In the big picture, I don't care how you did on it. You honestly shouldn't care how you did on it. Do you walk away with two things in mind? That the simple things can usually get you what you need. And number two, this is totally doable if you have a nice fundamental approach. Look at one thing at a time. Don't panic. How many of you had a panic moment? I don't know what's going on. There's no y-axis. Shit. These are the kind of things that happen. Practice keeps you in check. I hope that one of the things you pick up as you go through all this is you don't panic as much. You just address it. Basic things applied in a systematic way will get you good results. A few things are going to screw you on the test. It's going to happen. But by and large, there's a lot more doable things that you get overwhelmed by than there are impossible things. Okay. Based on this, how many agree this is a butt-kicking question? This just hurts people. It just does. I can pretty much figure that 20 of these 36 randomly guessed. And so it's one of those questions after you see the answer key seems easier than it really was, but it's challenging because it just throws people for a loop. Okay. Diprotic curves. Want to revisit this again? When you have two curves, two protons, you take them one at a time. How do I get the pH here again? pH in this point right here. Exactly. Average of pK1, pK2 averaged up. The isoelectric point is the one that's where the sweet ion exists. So in this case, if you only had two sites, the carboxyl terminal and amino terminal, then it's an average of those two. But it's always, equivalence point is always the isoelectric point where it carries no net charge. In this one, I'm not doing amino acids yet. So it's just two protons like carbonic acid, bicarb, and then carbonate. So I want to take that and apply it trial by fire. So screenshot if you want, but clicking in 3, 2, 1. So walk me through this, somebody. Tell me what your logic is. So how many, when you see this, decide there's more than one proton? Is that one of the first things you recognize? So how many protons for this one? Two protons, diprotic. Does that help me at all? Is that going to help me to eliminate some wrong answers? Okay. And is it strong or weak? Weak. How do you know? Has a lip. Perfect. Is that also going to help me? Okay, so if I'm looking at this right, you're telling me it's weak and it's diprotic, you said. 2 protons. So the fact that it's weak diprotic, hopefully I can zero in. Carbonic acid, how many learned is H2CO3, nitric HNO3, phosphoric H3PO4, sulfuric H2SO4. Are any of those strong? So how do you know the number of protons? Good question. How did anybody get the number of protons? Because I just took your word for it. It was diprotic. I never double checked. 2 equivalence points. Are equivalence points vertical or horizontal? Vertical. So I start up, I go flat, vertical. So that's the first one right there. The first vertical inflection point. So that's the first equivalence point. Then I continue, flatten out, and climb again. So 2 protons because we have 2 vertical lines in our graph. Oh, no problem. And how many do it that way? And honestly, how many do it sort of subconsciously? You've just sort of grown used to seeing the verticals. Horizontals, good question. So these are the equivalence points. What are the horizontal regions? The buffer region. PK1 buffer region, PK2 buffer region. So horizontals, the buffering points, buffering range, verticals, the equivalence points. So hopefully that seems okay. And good question. So I'm going to throw this back at you. Why did you ask that? Like what did it, or what does it do when you ask that type of question? And my tone, maybe, I hope my tone isn't sounding bad because it's actually a really positive thing. Yeah, half equivalence point is right in the middle of the buffer region. So the buffer region's here, the middle of the buffer region, the half equivalence point is the pKa, exactly. So what is the purpose for anybody who asks questions like this? Why do you ask them? Organizing the information. If you can see it in an organized fashion, horizontal, vertical, horizontal, vertical, horizontal, and you know what they do, is it going to be, if you're organized now, can you recognize things in context later better? So content review is 100% designed to get organized. Knowing a lot of stuff is useless. Knowing a lot of stuff in an organized way where you can access it is awesome. So I love the questions you're asking because are they pertinent so that when you ask it here, can you apply it in a future question? And those are the kind of things. So I'm hopeful that all of you do the same thing. And not to, I mean, both questions I think came up in private, but both were excellent questions. What the heck is going on? How do you know these things? Now, once you see it, organize it in a way so when I see it again, I recognize it. So I'll wait a second until another one pops up. But for this one then, talk me through it. So based on the weak part, what can I get rid of? So sulfuric is gone. That's a strong. The first proton is strong. And nitric, perfect, strong. So those two are out. Okay. How do I decide between sulfuric and, phosphoric and carbonic? Number of protons, perfect. So how many protons in carbonic acid? 2, 3 in phosphoric. This is diprotic. There's only 2 vertical So best answer, carbonic. Yeah, you actually technically have a right answer, but that would just be a more ubiquitous and inefficient way to get to the answer. But you're totally right. But it just, I'm dodging that one. Okay, so hopefully this one seems okay. And there is so much excess information on here. So let me get rid of, actually, let me just get rid of everything because I think all the structures now drawn up there. So if you want to screenshot this, this is a cleaner, better picture. In fact, let me at least write in nitric acid, HNO3, sulfuric acid, H2SO4. Okay, so that one might be a little bit, now, good screenshot. Yeah, so sorry to do that to you. And I sort of dodged it, but when I ran the or put the AAMC list at the very beginning, they have a spot, know your typical strong acids. So there is a certain amount of memorization. Yeah, know your strongs first and deduce your weaks. But strongs, by all means, you have to know off the top of your head. And then common weak ones that show up in OChem and GChem, both, like acetic acid, you should know is weak for sure. Carboxylic acids, you should know are weak because carboxyl terminals 2 to 3. Amines are weak. Protonated amines, so ammonium, and then protonated alkylamines. Yeah, so why is carbonic acid so frequent in the homework? So big picture, blood buffer, exactly. Because it's a physiological buffer and because it's in our atmosphere, CO2. It's just a major component. And then the other reason it's kind of cool, that is 100 grams per mole. Just because of easy math, that ends up on the MCAT fairly often. Totally obscure reason, but that's one more reason why these things seem to show up. Oh, and it is to confuse you. That's just a sheer bonus, but no, it's mostly because of the physiological systems. Same thing with phosphate. When we say inorganic phosphate, it's actually phosphoric acid that's been deprotonated. Okay. 40 seconds, good luck. Okay, honest answer before we do anything. How many had a bit of panic on this one? Because that's definitely a spot to you want to start. Like, what the heck is going on? I've never seen this before. Okay, have I seen anything even similar? Well, how many protons are in this mixture? One for this compound and one for this compound. So when I titrate a compound, do you agree? I take the strongest proton first, then the next strongest, then the next strongest, and so forth. So if I have one compound with 2 protons, I take the strong one first, then the next strongest, and so forth. But what if they're, instead of 2 H's from the same compound, what if they're H's from 2 different compounds? Does the base know any different? Oh, I haven't, no, for this one, actually, I responded to a private question. Yes, you got the right answer. So for this one, 2 protons, taken one at a time, just like if it was on the same compound. So tell me, are either of these 2 strong acids that you've memorized? Nitric is strong, nitrous is weak. So you take them one at a time. So is the first proton going to have a lip or no lip? No lip. So what can I get rid of? A and C are gone. Perfect. So no lip, A and C are out. Okay. How do I decide between these two then? I have a second proton. Which one shows the second proton? Mono versus di. Exactly. You have one proton for the first one, the strong one taken first, the weak one taken second. Best answer? B. How many get it, but confidence is the bigger issue, not knowledge? How many know everything we said? Nothing is new, but believing you know it. Is that actually a bigger battle than actually knowing it at this point? I have no idea. I'm assuming it's a titration of both of them already in there. So whether I add them together, one at a time, whatever, I have a mixture of these two, and I'm titrating a solution that has both of these. So both of them are in there. Yeah, going with the lip, it helps. Oh, okay. So you went the weak one first? Yeah, the weak one, the second one. So if I break this curve down, there's my strong curve, my sigmoidal. There's my weak curve. Has a lip, climbs, levels off. So, but you take the strong one first. So you do the sigmoidal first, followed by the lip second. Yep, exactly. They dissociate more completely. You get all of it. So it's the log scale. And those are the kind of things. So, and this is, let me throw this question back at you. You knew there was no lip before, and you just sort of said it, but it's now finally from your question is like, now you feel it. You went from knowing it and being able to regurgitate it on a flashcard to now like, I get it. Those are the moments you have to take 5 to 10 seconds to celebrate. Those are the ones that really matter, because when it clicks and it sticks, that's when you've truly learned it and it's part of you and you can apply it. But how many see this as a strong curve and a weak curve followed by excess? How many are starting to look at it that way? First proton, second proton, first proton, second proton. Hopefully that starts to happen. Okay, one more of these. So if you're screenshotting, I think the who got it right is going to pop up in a second, but if you're screenshotting, probably want to do it now. Okay. I have no idea where to start, so you're going to have to walk me through this completely. So Phyllis, you're up first. How many protons on this one? And again, I'm just going down the list, so I seriously apologize if and I know I hated being called on in class. This is so bad, but I'm just basically picking from my list. So how do I tell how many protons? Number of equivalence points or verticals? Okay. And by the way, if you just don't want me to ever call on you, say something. I do it because it's that sort of engaging thing and just little weak or just a tiny little feedback. I taught in a classroom for the first time in over a year and a half the other day. Just happened to be subbing in somewhere and teaching. And it was so wonderful and great to have faces and interactions and all that. And I forgot how critical that was to just call in people. And so I apologize that I know it's an important tool. and trying to use it. But if you don't want to be called on, I also need to know that, so I don't do that. So I'm picking from the list, and I'm trying to pick names that I normally don't interact with. So if you just want to be left alone, please let me know. But if you don't mind being reeled in, that's fine too. But how many agree 3 vertical, so 3 equivalence points? So this acid is triprotic. Does that help me at all? Sure. Okay. Can you name the triprotics for me? Oh, you can name sort of them, some of them at least. Can you tell me the basics? His lies are basic. I love who changed it. I know it's one of you because I used to write it all out. Histidine, arginine, or histidine, lysine, arginine. I think somebody wrote it like this. Lies are his. So the 1-letter code, I just loved. I'm so stealing that, by the way. But in this one, lysine, arginine, histidine, are those triprotic? Yeah, and you're right about this question. And then my sister has a glue asp. Kind of embarrassing. She sticks to things when she sits. My sister has a glue asp. So I've been embarrassed to let you know this. My sister has a glue asp, but you know, Todd's gonna lie. I don't even have a sister. Lies are his. By being male, I'm lying to you. But if I did, I know she would stick to things. My sister has a glue asp. So these are the ones that are triprotic. These are the 2 that we think of as acidic. These are the 3 we think of as basic. So can I get rid of alanine? Because it's not one of these. Okay, so alanine is diprotic. It is gone. Glutamic acid is one of these, so that's possible. Do I love leucine? Nope. So that one's out. And then lysine, yep, potentially. So you read, there's 7 altogether. Lies are his. My sister has a glue asp. It can potential. So I need the space up here for something that's going to pop on screen. So if you want to put this in, that's fine. I'm going to erase this. Yeah, exactly. Triprotic are ionizable, meaning they have a carboxyl terminal and amino terminal that can be ionized like everybody, but they also have a side chain that can gain or lose protons. So exactly. So that, I mean, that's exactly the definition. Spot on. Okay, I'm going to erase 3, 2, 1, erasing. And so now I want to look at this a little more carefully. Oh, you're welcome. When I look at this compound, how many learned the N terminal is around 9 to 10? So I'm just going to say my 9 to 10 looks like it's around there because that's above 7. And carboxyl terminal, 2 to 3. Carboxyl is always the lowest. So is this the unclaimed side chain? Glutamic acid side chain is around 4. So it's between 3 and 5. Lysine is around 10.5. So would you describe this as being around 4, or is this around 10.5? Perfect. So if it's around 4, what amino acid is it? Is it glutamic acid or is it lysine? Glutamic acid. What would lysine's curve look like? So let me draw lysines for you. Forgive my simplicity in this, but this is low, low, high. So lower than 7, lower than 7, above 7. Lysine would be lower than 7, higher than 7, higher than 7. So it would be low, high, high. Oops, so sorry. Dang it. So 1, 2, 3. Your pKs would be below 7, above 7, above 7. So low, high, high. For lysine, low, high, high. And for this curve, it was low, low, high. Does that make sense? Side chain is total memorization. And sorry to abuse you and make you feel bad about yourself, but dang it, you should know that for the amino acid lecture. So here's what you need to know. C, D, E, H, N, K, and R. Terrible at the alphabet. The C terminal, 2 to 3. D and E are around 4. H around 6. N terminal, around 9 to 10. About 10.5 and 12. Yep. Yes, yes, yes. Everybody read what Brooke said. Brooke, why do you say this is true? Totally true. Why do you say this? Every one of them has a lip because carboxylic acids are weak acids. Because every proton in there, the weak acid group, carboxylic acid, the weak group, the amine, and the weak group, carboxylic acid, imidazole ring, amine, guanino, whatever they are, they're all weak. So weak, 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 always. So Jonathan, do you have this list memorized yet? Dang it, as I call you out in front of everybody. Ooh, so talk me through this one. So Dr. Keki, did you come up with that? Because that is pretty good.
Oh no, it was from my biochem class. It was like Dr. Checky, and then North Carolina is like the amine terminal, and then the carbonyl terminal.
Pretty good. So the only ones that I am a little, I'm gonna add it, and I'm gonna put them in a slightly different way. So why am I omitting? Why am I just doing Dr. Hem? Oh, Dr. Heck, excuse me. This one is usually tied up in a disulfide linkage, so I usually don't see it. It is fair game for titration by all means, and that's why I had it in the my sister has a glue asp. And then why is about 10.1? Physiology says we aren't really going to get that high realistically, but I do agree that those should be included if it's just a free amino acid. If it's a protein, we kind of ignore them. And because for this one, I should have had them in there because I'm doing a single amino acid. But that's a really good mnemonic. And again, thank you to everybody, you in this particular case, for tossing it in there, because do these things definitely help? Like Tiffany dropping snowflake yesterday, or snowdrop, excuse me. Those things are just awesome. So when you have mnemonics and you share, we all do better. Okay. Hopefully this one seems okay. This is a tough question, if you ask me. Would have been the question from hell had I had both aspartic and glutamic. Yeah, cysteine is around 8-ish, exactly. So I should put this around 8.4. So 8.4 I'll put, just to be really anal. You could not have done that. If I would have put aspartic glutamic, no way. Just like if I were to put both lysine and arginine, would have been really tough. So it had to be one of the low ones and one of the high ones, and then a couple diprotics for this to work. So I kind of did the hardest possible version up to that threshold of impossible. So hopefully seems okay. So full circle back to where we started. Indicators. Indicators, not a lot. Oh, sorry. So question. Yeah, so they have a carboxyl terminal and an amino terminal, like all amino acids for their two, but they happen to have a side chain. Lysine side chain is an amine group, which happens to have a pK, in this case, 10.5. And then glutamic acid has a side chain of a carboxylic acid beyond just the carboxyl terminal. So that's a third proton. So every amino acid always has at least 2 amino and carboxyl terminals. And then those 7, Dr. Checky of North Carolina, and I'm just gonna do Dr. Checky. So what her mnemonic is the amino acids that have a triprotic are D and R, which are aspartic acid and arginine. And then cysteine, histidine, glutamic acid, lysine, and tyrosine. So actually, that's such a great mnemonic for the triprotics. So again, thank you so much. Marissa, that was you. We toss it in, I think. Okay, I'm just gonna keep scrolling. Yeah. So thank you. But sharing isn't the pre-med way. This is causing confusion and discomfort, but it's still awesome. Okay, we use it for 2 things. Yes, exactly. So every amino acid is weak because every proton on it is a weak functional group, and the lowest pK is 2 to 3, and so strong acids are always negative pKs. And then yeah, and see, this is what's sort of interesting in biochem nomenclature. And this is also what is kind of a complete pain in the butt as a teacher, because they name things in such a funky, weird way. Technically speaking, can a compound be either acidic form or basic form? It could be either one. And so we talk about, let's just take the acidic ones, glutamic acid, aspartic acid. Do they exist in our body as glutamic acid and aspartic acid, or do they exist as aspartate and glutamate? They actually exist in the conjugate base form. So the acidic amino acids are actually bases in our body, and the basic amino acids are actually acids in our body because of where the pH lies. And so because of this, there's just room for all sorts of confusion. And so they name it acidic and basic based on what they are when they're neutral. So aspartic acid and glutamic acid from neutral will lose a proton, acting like acids. Lysine, arginine, and histidine from neutral will gain protons, and in doing so, they're acting like bases. So the name they assign to them really isn't, honestly, isn't as useful as it could be, but we still keep on saying. So. Oh, thanks for the private message. At this point, no. It's just, ages ago it would have been awesome, but yeah, it just had this discussion already, and it's falling on deaf ears. So it is what it is. So thank you though, appreciate that. Okay, indicators. How does an indicator work? I'm so confused by what an indicator does, but luckily you're going to teach me some OChem. Is it possible to get color in an organic compound? Can organic compounds somehow exhibit color? And what's the right answer to everything in OChem? What is the right answer to every question? Resonance. You nailed it. If you have enough conjugation, if you have enough resonance, then instead of absorbing the UV like a normal carbon-carbon double bond or carbonyl, if it's enough resonance, it can actually absorb in the visible range. So what if I had a compound that could do this? Let's say when I deprotonated it, it turned into O minus. What if the O minus could kick in and there was a double bond there? Okay, so when it kicks in, what if it could kick there? And maybe that would knock a double bond here out of the way. That bond then go like there, and maybe kick out something like that. So would that be reasonable? So I'm just adding weird things to this, but would that be possible to suddenly go from benzene ring conjugation to all of a sudden there? And I'm just piling on, but how many would agree if it did all that, I would have this compound? Something like that. Did the conjugation increase when I took this proton off and it kicked across? Did it go from 3 pi bonds to now 4 pi bonds? Did the conjugation change? I mean, how many agree 3 pi bonds compared to 4 pi bonds? Is that different conjugation, different resonance? And so this is just an obscure example, but if I do something like this, if I change the pH, then could it go from not quite enough conjugation to enough to be colored, to go from clear to pink? Okay, that's the last of the outcome I want to do until we do spectroscopy. But if you have enough conjugation, it can be visibly active, absorb light in the visible range. So it can go from clear to pink. So here's what's going to happen then. I'm going to erase this. Let's say, again, it's a phenol. So I'm going to just focus on phenolphthalein, which I just sort of did. And I'm going to leave the rest of the molecule like that. When it gets deprotonated, I'm going to leave it as O minus. And I'm going to not worry about the resonance here, but it's going to go from clear to pink. And it has a pKa around 9.5-ish. It's like 9.2, but I'm going to go with 9.5 just to have it like middle of a range, which means this curve, the pH is low, 7, that's well below, not going to change, not going to change. But when it goes up to here, if this is 7, this is around 9.5, is 9.5 where it's going to be clear, pink, or an average of the two? Average. So what happens is the solution is clear, 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 and all of a sudden you get a slight change. And so right there, the 9.5, that's where it's kind of half and half. So is it gradually going from the clear form at lower pH to the pink form at higher pH? And so the key thing to remember, when pH is higher than pK, it is deprotonated and pink. When the pH is less than pK, it's going to be the clear form. And when it's around pK, you get a mixture of both. So you can go from clear to light pink to dark pink to purplish. So if I can pick this the right way, can I get a change to occur just when I need it? And then also I want to revisit something. How realistic was it that they wanted you to be able to tell that pink instead of that pink? I mean, the difference of a half drop is between here and here. How many agree this lab is BS? I'm sorry, this is me just venting, but good luck being able to tell that pink from that pink. And I've yet to meet anybody that good. In all the years I TA'd labs, never. Okay, in both years I TA'd labs. Just didn't meet anybody who was that good at distinguishing it. But it does go from clear to pink. Luckily in the MCAT, you just have to know the following. The best case scenario, you want the pH to equal the pK of the indicator, because you want the middle of this change there. But just like a buffer, you get about a plus or minus 1 ratio. And then want to revisit the pH at equivalence is pK of the acid plus pH of the titrant base divided by 2. You want the pH at equivalence to equal the pK of the indicator. You want this to be true. The plus or minus 1, I've now turned into an almost equal then. So instead of saying plus or minus 1, I'm saying it's roughly equal. This is what I want you to take home as your message. So let me just ask you the following. If I'm doing the titration of HCl plus NaOH titration, what is my indicator pH needed? What indicator pKa do I want? Perfect, around 7. If I'm doing HOAC plus KOH, I want my indicator pK to equal. Greater than 7. Perfect. Why do you say that? Absolutely 100% right. The answer I was fishing for. HOAC is a strong or weak acid? Perfect. Weak acid, strong base. So I want it to be maybe around 9-ish, plus or minus. Key thing, greater than 7. So does that make sense? You pick the indicator to match what the pH equivalence will be. Okay, not bad. And then the color phenomenon, just know that it has to do with organic species. How soluble are organic molecules in water? Exactly, not very. So even if I wanted to put more in, can I really only put a drop in before it becomes insoluble? So we usually dissolve it into like ethanol, and hopefully a little bit goes in, put a drop in there, but we can't put much more. Okay, that said, pH approximation. Want to go back to what we said earlier, and that was at the very start, and that is, if it's blue when protonated and yellow when deprotonated, then green is in the middle. So I'm going to say, if you had a situation where pH equaled pKa, half of it's protonated, half it's deprotonated, half and half. Do you agree? Half would be the blue form, the protonated. Half would be, I'm sorry, the yellow form, the protonated, and half would be the deprotonated, the blue form. So end it with green. If you have a little bit more, then I'm just, let's say it's 1 unit above, that's a 10-to-1 ratio. 1 part yellow, 10 part blue. That's really green with a slight hint of, I mean, it's bluish with a slight hint of green. But this chart's overwhelming. I want to just point out though that it's 1-to-1, so green. 1-to-2, it's still basically green with a little bit of blue. 1-to-10 now becomes blue with a little bit of green, and so forth. And so let's say, for sake of argument, this was, let's say, 7. So if this one was 7, then that would mean 9 is around here, 7, 3, 8, 6.7. So in other words, can I guesstimate the color and pH correlation? So if I test water, let's say you want to go swimming in a public pool. And actually, you don't know if there's a generation gap, but how many know what a public pool is? Okay, good. So for those of us who've been in public pools, do you agree sometimes younger members of the pool population tend to add a little bonus fluid to it from time to time? So they have to add in chlorination, or they chlorinate it, and they kill off the bacteria, but can that chlorine turn into hydrochloric acid and hypochlorous acid and change the pH, and they have to modify it, which means, are they putting acid into it, making it kind of a moving target for me? So they put the acid in to kill off the bad stuff, then they add base back in, they might overbase it, underbase it. Oh, I'm glad they do. Oh, well, okay. Where I was at, do you honestly think the 15 or 16-year-old kid hired as a lifeguard truly tested it every hour and then had the courage to tell a bunch of angry citizens from the town to get out of the pool? Yeah. So in theory, it was tested, but yeah, I don't know, but whatever. I mean, it is what it is. But can you test it to see if the water's green, would you swim in it? Sure. If it's blue, a little too basic. Would you swim in yellow water? That's a good rule of thumb for everybody to get the right answer for. Do not swim in yellow water. Good rule of thumb, it's too acidic. Okay, I want to take this concept here and apply it to something a little more elaborate that's been on the test a couple times. So I'm going to say 2 things we can do. We can detect the endpoint in titration where we have the pK of the indicator equal to pH at equivalence, but also we can do color to pH. So once upon a time, maybe they had a passage where they had indicators A, B, and C on the stick. And I totally, to avoid copyright issues, are calling them X, Y, and Z. And they might have given you a table that said, here's the pK, and they told you what color it was when it's protonated and deprotonated. How many know that yellow, red, and blue are primary colors? Okay, this becomes important because we want to have a transition color. So what do yellow and red transition through? So yellow and red transition through orange. Yellow and red mixed together to make orange. But blue is a complementary color of orange, so you're in the ballpark there. What do yellow and blue mix to make? Green. And then red and blue? Violet, purple in color. So when you see this chart, really, it's this chart. So when the pH is low, more than 1 unit below, it'll be yellow. When it's high, more than 1 unit above this, it's going to be red. But as you go from 4.02 to 6.02, is it going from kind of orangish yellow to yellowish orange to reddish orange to orangish red as you transition? So how many can see this sort of attempt at color transition I tried to do with the lettering? If that seems okay. Yeah, this was, okay, you ever get so obsessed with something you get out of control and you end up wasting way too much time, so everybody better friggin' appreciate it or else? Not that I'm saying that happened, but yeah, this was just way too much time. Dumb things you do. Yeah. Oh gosh, yeah. Although what you're calling old school was so, you want to go old school, my crayon box had 8 colors. So I'm trying to, generationalism. There we go. Okay. Thank you, favorite student. So somebody just responded in private who has just become favorite student, and a bet above all of you who didn't say the wonderfully nice thing that was about this color scheme. Okay, let's apply it. I dip a stick into some solution and I analyze this, and you tell me which is the most important color, orange, yellow, or red, for deciding what the pH is. Yeah, I'm just ignoring your question, Brooke, because I don't know if we even had that. Why is orange most important? Definitely right. Stephanie, why do you say such a thing? Yellow and red are pure colors, but this is a mixture. How many agree a secondary color, a mixture color, is in a range? This just tells me high or low, high, low, but a mixture tells me somewhere in the range. So would you describe this as yellowish orange, reddish orange, or orangish orange? This is orangish orange with a hint of orange inside of it, which means, is this probably right about in the middle of that range? Sure. So can I say this is probably around 5.02? This one simply tells me it's less than 5.93, which fits with what we know here. This tells me it's less than 8.07, which again fits with what we know from this, 5.02. But is a secondary color more important than a primary color? Okay. 2 questions. For this next strip, is the pH higher or lower than from the first strip? And what is the pH for the second one? Oh, for this one, you mean? Yeah, there's a couple questions that correlate to this one. Oh, no, they did not give you this beautiful chart. So yeah, we're gonna go back and do a couple questions based on the ugly chart. So this one I'm trying to push to get that visual, but yeah, unfortunately, and I don't know why. The MCAT is a black and white test except for backgrounds, shading on charts and so forth. But for anybody who's taking the MCAT, would you agree the data is basically black and white? All the drawings, basically black and white, or useless colorization. I don't know why. The only explanation I ever got was somebody from 20 something years ago who was basically saying that they don't want to bias it against colorblind people. It's like, give me a break. With all the biases you have built into your system, suddenly colorblind people matter, but it's just, that's what they said. I think it was probably cheapness of printing back then, and they just carried over to computer. Anyway. Oh yeah, I don't mean to totally fire the shots, but it's just, Yeah. Okay. So, oh, paper was such a more pleasant experience, less stressful. Honestly, I just think there was much lower stress. And you all start at the same time, finish at the same time. You take breaks together. It's a family. It was a family affair. It really was. So for this one, what's the most important color? Red, green, or red? Yeah. So, and that is so. I mean, I knew as I was saying, and remembered. Oh, that's right. We have I think we have two actually colorblind people. So I apologize that I've singled you out and oppressed you, but this is green. Where would green fall? So between yellow and blue. So is green the one that I'm now in the middle of the range? And would you call this yellow or yellowish green, bluish green, or greenish green? I just love saying that. But how many degree? This is smack dab in the middle of greenness. So greenness in the middle would be how many degree? Maybe 6.93. So the pH is definitely higher and the color scheme has changed. And then finally, that last one, can you get an exact color or is this beyond the range of the indicator stick? How do you know it's beyond, Brooke? What makes you say that? There's no secondary color. Everything's a primary color. So it's above 6, above 8, and above 10, basically. And note again, PK plus 1 and PK minus 1 are the ends of the range. So the range is usually plus or minus 1, just like with buffer regions, indicators roughly there. Every indicator is a little different. So some might be plus minus 0.8, some might be plus minus 1.2, but it's roughly in that same area. Add some acid to your pool. Do not dive in that thing. You will die. Perfect. So how many are okay with this like color correlation to pH? Only now it's not visual, it's going to have to be words. So with that in mind, if you want to screenshot this, feel free to. I'm about to click. 3, 2, 1. So back to the chart you would actually get on the test. So one answer in. How many agree it starts lower than the lowest and finishes higher than the highest? So X is my lowest one. So it should start 5.02 minus 1, about 1 below the lowest, and go up to about 1 above the highest. So 5.02 minus 1 is around 4. 9.07 plus 1 is around 10. So 4 to 10. Perfect. Hopefully it seems okay. So one more question. And this is where I diverge from the handout, so I apologize, but this is numbered differently. Oh my gosh, I have no idea. I have no clue what I did, why that's on there. Yeah, maybe. I don't know how I think I cut and paste this one and I must have like screwed up and through the whole document. Okay, so I'm gonna have to get rid of this. I have to exit out and see what the heck I did, because I'm gonna need that space in a second here. Oh my gosh, I cannot grab it. So hold on, I need to do something real quick. Okay. Whew. Sorry that was just so random and weird. Okay, so for this one, is this estimating color to pH, or is this figuring out the endpoint in the titration curve? What's going on in this one? Titration curve. We're figuring out the endpoint in titration. Perfect. So therefore, tell me about this titration. What are we titrating? What is ammonia? What is hydrochloric acid? Perfect. So tell me about ammonia. Is that a strong base, weak base? And this is ammonia, not ammonium. Weak base, titrate by a strong acid, exactly. So we are titrating this by this, meaning we're starting with this and adding this. So tell me two things. What is this compound, weak or strong? This is your weak one. This is your weak base. So it's going to start high because it's a base and have a lip because it's weak. And you're adding in a strong acid, so pH is going to go up or down over time. It's going to go down. So would you agree your curve is going to look something like this? And because it's weak base, strong acid, acid dominates, so it's going to be pH below 7 equivalents. So I'm okay with the curve looking something like this. Does that seem reasonable to you? Okay, perfect. And we're going to start with NH4 or NH3. I'm going to finish with NH4 plus. Okay, so the equivalence point is down here. This one is 4 to 6, this one's 6 to 8, and this one's 8 to 10. So let's go ahead and put those in there. So X, this is the range for X, this is the range for Y, this is the range for Z. Okay, so based on that, which one fits roughly where we're looking at it? X is working out. Z is definitely way too high, out of the range. So I want the pK of the indicator to match pH at equivalence. Yeah, you kind of do. And I think just through homework, I think making conscious effort to memorize them now is pointless. Making an ongoing list as you go through questions ends up being a little more useful, especially double AMC material. So don't stress if you don't know them now. Be a little bit perturbed, but don't lose sleep over it. Lose sleep down the road. Okay, so for this one, Z is out, too high. And then X, although part of it's below 7, this is a better one. Quick estimate. What is the pK for ammonia? And if you don't know it, tell me what the amino terminal is, roughly. 9 to 10. Perfect. And tell me what the pH of a strong acid is, roughly. 1-ish. Perfect. Carbonyl terminal will be that, but 0 to 1, 1 to 2, somewhere around there. So most of you said around 1, so I'm going to say around 1. What is the average of 9 to 10 and 1? Around 5-ish. Perfect. So if this is around 1, like you said, this is around 9, 9, 10, like you said, averages out to be 5. Perfect. So around 4.5 to 5.5, somewhere in that range. So hopefully that seems okay. So estimating the pH at equivalence, again, do it by the pK and the titrant, average the two out, and you're in the ballpark. It's not perfect. This is not an exact number because this is a guesstimate number, but you're in the neighborhood. So best indicator, indicator X. Hopefully it seems okay. So one last thing to complete, and that is to let you know the clock indicates the class's endpoint. So again, I always end up going over, just online, I always go 10 minutes over. I don't know why, 10 to 15. It just, things go a little slower, but this covers it. I hope you have the foundations to now go and try some of the homework. And if you end up going to titration next week, own it. Just have everything down pat and get all the questions done like in your mind going through lecture, just nail it. So how many use this as a pre-lecture to instead of reading, to be better suited for the standard lecture. Yeah, and that's hopefully that puts you in the right frame of mind so I don't mean to make it like in lieu of, I make it in addition of or prep for. And he goes in different ways than I would. And so hopefully you end up getting like two different, I guess, perspectives, which it just makes it more clear. And so I'm always going to try to do one of the ones he's doing a week in advance, although next week it ends up getting funky. So let me email you. I'm away from home. I'm like at my daughter's house doing the lecture. So when I'm back, I'll email you, let you know what next week is. But I think I might be starting into either sound or light or circuits. I can't remember one of those, but I'll let you know what it is. I'll give you a better heads up. So anyway, this is the end, and hopefully you're in a good, happy spot, and homework will be easy. Happy Friday. Electrostatics. Okay, thank you so much. Oh yeah, so appreciate that. So Jonathan, you put everything on the website for everybody, or on the Discord site, right? Perfect. Okay. The one thing that's going to change on that, because I ended up getting to give the lab techniques lecture yesterday, just squeezing that thing in worked out well. I'm going to fill in that other topic, maybe with carbonyls or might rehash sugars. It's just going to come down to what your consensus opinion is. Oh, thank you. I mean, all that. And again, I do, for the two of you, or I think three of you, I called randomly on just because I wanted to pull names in. I apologize. And again, I will try to force everybody to get involved, but if you don't want to be, don't. I mean, just let me know and I will. Yeah, you're getting access to the online exams, but I don't know why there's like some special celebratory date, because it's still way too early to be doing them. But yeah, you can at least check. You should log on to make sure your account works, because there's often a typo or two or three in the entries. So there's always one or two people who can't get it right away. Yeah, make mistakes now is perfect. Oh, so is taking notes on the iPad really hard? Oh, so that's why. Yeah, so you're doing that. I recommend full-length exams about 5 weeks before your actual test date. So you've reviewed enough to have the information and you can take notes and put it all in place, but you still have 5 weeks to learn from the experience. And I would start with their sample test, because that one is it's just a great introduction to the way they ask things. And you will find out their test is a little bit different than ours. And yeah, and the thing is, how many of you are behind? I think that's the beautiful thing about Discord, is how many of you vent every day, I'm behind. I'm never going to get caught up. Yeah, and just knowing that everybody's in that same boat. And part of the realization of your studying is, I don't need to study everything. I need to study what I need, and that helps. I don't think third party is useful right away. I think AAMC sample test is great, then third parties, and then finish off with a AAMC 1, 2, 3, and 4. But it's just AAMC material is so much more indicative of the test. Even though the difficulty may be higher in one case, lower in another, it's still style-wise the best representation, especially psych, soc, and cars, that you want to do that. You want to save those for the end, but you also want to do section bank. So section bank stuff, probably want to start about 6 to 7 weeks before. Yeah, and the thing is, it's just guilt is such a powerful force, and maybe it's a good thing. Maybe it gets us to do stuff, but yeah, you're going to feel behind, and you're never going to feel caught up ever. You're going to feel less stressed about it, hopefully, with time, and take care of each other. Yeah, I mean, just be kind to each other, and the world is so much better. And I don't mean to sound like pseudo or hyper Berkeley, but we're too mean to each other right now. You guys give me so much hope. you share with each other? Just, I mean, you seriously give me hope that the world is going, the pendulum is going to swing back, and you guys have to push it back. Yeah, I mean, what Jonathan, what you've done with Discord is so awesome for everybody. Yeah. So, and it just the positive feedback. And honestly, you guys are going to be able to answer your questions sometimes better than a teacher, because you know where people are going off the rails better. Teachers sometimes are too far removed from the material, and certainly from the stress you're going through, and you'll see things more clearly. So just glad you guys are supporting each other as well as you do. It's awesome. Anyway, okay, I'm going to go ahead and exit out then. I'm going to jump on one of these wonderful LA freeways.